Okay. So in this talk on initialization, optimization, and regularization, we're going to see a few sections. So first, we'll talk about network initialization. And thus far, you've been able to optimize your networks because under the hood, JAX did initialize your variables for you. And the first part of the talk is we're going to see options that people use to initialize the networks, and what other frameworks use, and typically it's a good idea. So the outcome is going to be that typically it's a good idea to stick with your framework's default. Then we'll speak about network optimization, because so far everything that has happened was straightforward gradient descent, but there's more involved, more advanced versions of the method, and we'll see two of them today, RMSProp and Adam. And Adam is the default that we should all be using in the future if we start. Okay. Then we'll see what overfitting was. You saw this again already in the second week, but we'll have a little recap on overfitting, then go into regularization, and finally there'll be code snippets that will hopefully help you use Adam in your code. And then I'll pass the word to Lokesh, who will do units. Okay, so why do we speak about the topic in general? We've already heard that network optimization is not convex. We are not guaranteed to find the global minimum. And because it's not convex, it also means there's bumps. And sometimes our cost functions aren't well behaved. So that means there is a lot of room for heuristics like momentum and other tricks that may help us get closer to the global minimum. Yeah, and that's also why initialization is important. If the problem was convex, if we had a cost function that only had one single global minimum, it wouldn't matter where we start. But precisely because it's not convex and there might be a local minimum somewhere nearby, the starting point can change the outcome of what it is we're doing. And all of today's talk is actually still discussed in the literature. So if you go to any of the big machine learning conferences, you will see new developments. So the science is by no means settled, and today's talk is an attempt to pick the most important developments for you. But if you come back in 10 years, you should look for the update, is what I'm trying to say. So people are working on this every day. Okay. So a classic initialization scheme is the so-called Glorot optimization, which comes from this paper here. And the idea here is to use a uniform distribution that is scaled with the input and output dimensions. So if we're looking at a linear layer, if we have an n cross m matrix, then we can use the m here and the n here to find where our uniform initialization should start. And the same goes here for the upper bound. And precisely because we do not yet fully understand the mathematics of deep learning, the authors empirically verified this. And it's worked well ever since, and it's typically an option in most machine learning frameworks. So that's why we are talking about it here. And what this means is that if we have our uniform distribution here, that means we have the upper bound is going to be here. The lower bound. And then the upper bound, if that's the upper bound, is going to be here. And then we would see an equal distribution of numbers in between the two bounds. And this works well because it is bounded. So unbounded initializations don't work well. And some of you have chosen unbounded initializations by accident and have learned the hard way why we want a bound here. Because if we don't, especially normal distributions have long tails, and that means that you can end up with a very, very big or very, very small number. And if you're unlucky, that's going to cause an underflow or overflow later in the optimization process. Right, so then this, the so-called He initialization, which you're also likely to see, is a simplification of the Rho-Kois. They simply drop the n here. And this is the default in PyTorch. We're using JAX, and the JAX default is coming. But if somebody was training something in PyTorch, then they are using the He uniform initialization under the hood. Yeah, and it's important to use these standardized initializations, because then hyperparameters for your optimizer, which are also typically preset for you, are going to work well. Right, and unless, yes?
Sorry, can you say again which is n and which is m?
Here was the number of output dimensions of the layer.
Okay.
Sorry, I was too fast. Yeah. Right, and that means the numbers haven't changed. So here, this is m. So this is the input dimensions for the He initialization. Okay, and then what are we using? So if you are using in JAX and Flax, people use the so-called LeCun normal initialization, which is a truncated normal distribution. But the key here is that we are redrawing outliers, and we consider outliers if they are larger than 2 standard deviations away from 0. And that's an important detail because it removes the long tails of the normal distribution. So in other words, we have a, if this is our normal distribution, something like this. If we are bigger than 2 standard deviations here and here, I'm not sure where this would be, we don't want any of those. So they're cut, and then we redraw them from the center. And this is an important detail, because without this hack, I'm going to call it a hack, the training wouldn't be stable. In some cases. Most of the time it perhaps might be stable, but you always run the risk of picking a very, very big or very, very small number, and then training blows up. And especially this is also important because the deeper you build your network, so the more parameters you add, the higher the chance will be that you will end up with an unstable initialization if you don't truncate the normal distribution. Right, but I think for us, we can typically stick to our framework's default. Unless we're interested in doing science. And there's a lot of science to be done here, because to the best of my knowledge, we currently don't have a solid theory for initialization, which means there's still a lot of room for math research to be done here, to find perhaps initialization that's provably better than some other initialization, which we don't have at the moment. At the moment, this is all very heuristic, because people have learned that these distributions work experimentally. Okay, yeah. So now we know what initializations exist, and for all practical purposes, we want to stick to the default, because all other hyperparameters have been chosen such that they work with the default initialization. And if we change the initialization, we also have to change everything else. Yeah, and then you also want to standardize your input, because that's the assumption that also goes with this whole initialization philosophy, that all of the gradients in the later computations scale well if you remember to standardize the input. We spoke about this already, but I'm going to say it again, because if you don't do it, then all bets are off. Sometimes it works, sometimes it doesn't, and it can be very painful if it doesn't work. Right. Yeah, so it's this, people investigate this, and it's usually a good idea to stick to your framework's default. but now we know what the defaults are. Okay, so now we've seen how to get started, how to fill our mathematical construct that we're optimizing with numbers. Let's think about better ways to optimize it. So up until now, everything that we've used was gradient descent. And now there's a little complication in the notation. So I think at this point we have to introduce this theta vector, which is a completely artificial construct that the theoreticians in the literature use to denote the vector of all optimizable parameters. So if you would go through your network and you would collect every number from every matrix and every bias term from every bias, and you would put them all in a big fat vector, then that's theta. And that's of course not useful in practice, because in practice you want your parameters to be in a dictionary where you can easily access everything and figure out what's where. But in theory, the theta vector makes a lot of sense, because then a lot of mathematics can be used, and there's of course nothing stopping us from taking all of the trainable parameters and putting them into a giant vector, even though there's no practical reason to do it. But yeah, we could do it, and then the math that people write down would work. But of course, it also works if we would consider a dictionary here. I think in most cases that's true. Okay, so this is how people write down gradient descent in the batched version. So the little m is the batch mean that most of you already implemented yesterday. And then we have a step counter theta here. Okay, so this, and then, yeah, of course, gradient descent was to get parameters, the alt parameters at the next step. We take the parameters from the previous step, and then we subtract the gradient times our step size epsilon. Okay. And the first modification, I think somebody of you, I think it was you, already thought about this. There's no reason for our step size to be constant. We could, for example, have a linear decay up until some point where we continue with a smaller learning rate. And please, this isn't 0, so maybe I should relabel this y-axis. So here we still have 0.1, I think. Or, yeah. So this is a non-zero learning rate. And this is already also implemented for you in most major frameworks. And it makes sense. So we're not going to do a lot of fine-tuning in this course. But if you have picked a problem where you want to apply deep learning, and perhaps you want to publish results, you want to publish the best possible numbers. And sometimes to get them, having a learning rate schedule, for example, like a linear decay like this, is a good way to get there. And the idea is that you want to start with a big learning rate initially, and then decrease the step size as the optimizer approaches the minimum. And if you remember the videos from day 2, sometimes we end up in a situation where here's a minimum, and then perhaps there's a valley around it. And if the optimizer has a too big of a step size, we can get stuck here. And because the step is too big, we end up here. And here the gradient turns around and brings us back here. And momentum is one way to tackle this. But if the learning rate is too big for this last little dip in the cost function, a decay would solve this problem, because then we would fall into the hole here as the learning rate decreases. Yeah, and then we already saw momentum. This is a classic approach to overcome local minima. And the idea was to introduce this moving average equation here in number 8, where we compute a running mean of some kind of all of the gradients. And that, I guess you guys implemented it on day 2, so we don't have to speak about it a lot longer. And but to remind everybody, it gave our optimizer this notion of of momentum, so that we would go up and then fall down again, and then eventually it would settle somewhere. And momentum is a key idea that people have extended. Right, yeah, oh good, I have a slide for the effect of momentum. So this is a nice situation. So if we don't have momentum, we would, settle back and forth. And we want to integrate these little arrows here into a mean direction. And that's what momentum can do for us. Okay. Historically, when people were working with recurrent connections, and we don't know yet what this is, but recurrent connection is when you have a network that gets an input, xt, but it also has a memory of some kind. Let's call it ct, and has access to the memory. And that means that there's some internal mechanics here, and situations like this create a very challenging cost optimization environment. And it was very hard to optimize this for a very long time until people came up with RMS prop. So RMS prop works very well in this situation. And the idea here is to make the learning rate adaptive and rescale it with this term R. So now we still have the learning rate epsilon, but now we have this little delta for numerical stability, and we rescale the learning rate with this average of the square g, which fixes instabilities in gradients like they can occur in this case. So it's has a smoothing effect on the steps on the gradients that we have, and this is important because this is the default optimizer that we should all use when we start. And I know it's a big equation, but it's easy to use because this is already implemented for us. This was invented by Kingma and colleagues in Amsterdam at the Vrije Universiteit, and they came up with a combination of momentum and RMS prop. So that's what it is. So they have momentum terms here for g and the square, and then they've introduced scaling terms for both, RMS prop style scaling terms. And empirically, this is the optimizer that works best, and it can solve a lot of problems with initializations. Sometimes it even converges if people forget to normalize their inputs. So Adam does a lot for us. It's what we should use for the rest of the course. So up until now, the idea was to implement gradient descent yourself and get some experience a little, play yourself with it. But from now on, we are allowed to use optax.adam, which is the default implementation. Okay. So this brings us to the optimization summary part. And I'm guessing the main takeaway is that Adam often runs reliably for a wide range of problems. And that's what we should start with if we are faced with a new problem. But the best optimizers don't help us if we are overfitting. So if we have this very fancy optimizer, we are running the risk of doing too much. And this can cause us problems. So what was overfitting? And you saw this already, but here's a little reminder from the deep learning book. Overfitting happens when the training loss continues to fall, but the validation loss starts to rise. And this means that our network starts to remember parts of the training data set. So even though the optimizer is still optimizing, the network parameters are assuming values that are specific to the problem that we're looking at. And what can we do against overfitting? And by far, the best way to tackle overfitting is to collect more data. So the more training data you have, the harder it is for the network to memorize everything. So this should always be our go-to choice. Unfortunately, it's also the most expensive choice. And in some cases, maybe the device that we had when we collected the data was sold or is broken, and we have to live with the data that's there. So in that case, we can consider extensions to the data that we already have. And a first straightforward idea is to add a little bit of input noise. And that's a nice trick, because then the input noise will make every image a little bit different. So that means if you're running over multiple epochs, so an epoch was one pass over the entire training data set, if you have a little bit of input noise, the same image will never look the same. And because if every pixel changes a little bit all the time, the network can't remember exactly that image. So that makes it harder to memorize individual inputs. But there's better ways, and for example, for images, but similar transformation exists in the audio world, or in your specific world, you'll probably also be able to think of transformations like this. A very nice or very elegant solution is, if we're dealing with images, let's consider the horse again. This is like a little horse, and we can randomly crop from this image. So we could take this image in one epoch, and then maybe this image later. And that way, we're fooling the network to some degree, because the background will always be a little bit different. The horse will always be at a different location, and that reduces our chances of overfitting to this particular image. Similarly, we can flip this. We could also, with a little bit of code, we can flip the image. We could give it this horse to look at, even though it's the same image. Now it's harder to remember the specific, and it's more likely that we're trying to force the network to understand what horses look like and prevent it from remembering this specific horse. That's the idea. Right, so left-right flips, I mean, in principle, you could also do up-down flips, but that's often a bad idea. So we don't gain much from this horse, right? So this, even though in theory this might be interesting, this is not likely to show up ever in practice. So up-down flips are often not interesting, but in the lab, who knows, right? If we're looking at cells from above, then up-down flips are great. Probably they're, I mean, I don't have a lot of lab experience, but I'm guessing that you can do that. You can flip it a lab image up and down, and then it's still a valid image. Yeah, and then we can also rotate. So that also wouldn't, I mean, could be, right? If it's on a mountain, this might be a realistic image for the horse. So random rotations, small random rotations, right? At some point, if it's too much, it's not going to help us anymore. But yeah, that's also an interesting idea. Right, and the general idea is to avoid that our network sees the same stuff again in future iterations. And if we can't measure more, we can always use input transforms like this. Okay, and if that also doesn't help, then it's time to regularize. And from the linear algebra day, you guys have already a little bit of an intuition what the idea behind regularization is. We saw the Tikhonov case, where I think there was a signal like this, and if we weren't careful, then our model would track the noise. But that's not what we wanted. We wanted the noise-free version of the function without the oscillations. And this would be, when we're tracking the noise, we would consider that an overfitting problem. And if we can't extend our data set, if we have to live with what we have, then regularization is a way to tackle this problem. And there are a few important ideas that are specific to deep learning, but L2 norm regularization is Tikhonov regularization in the machine learning world. And the idea is to measure the 2 norm of the matrix, which is the largest singular value, and attach it to the cost function. So with L2 norm regularization, the cost function changes. If we had our complete cost function of our parameters, and then we would have inputs and outputs, would now be whatever our task-specific cost function was. So perhaps a cross-entropy function, right, of the parameters x and y, plus now the L2 term. And here people typically introduce a little regular parameter that allows you to adjust the magnitude of the L2 term. Right, and then here we would use the norm, but I'm just going to write down, I write this more like abstractly as CW of theta. And yeah, and maybe excuse here, yeah, this is like mathematically speaking, this is not ideal that I put norm of the matrix here, but this is how you would implement this in practice. But it's probably, it would have been better to use the norm of theta here to follow this abstract idea that we have one big vector with parameters. Actually, no, I think this is okay. So this I goes over all of our weight matrices, and then we sum them up. And the weight matrices are, of course, part of our big vector theta. Okay, that's one way to do it. And then comes dropout, which is, the first time I saw it, I thought it was completely crazy. But the idea is very, very interesting. And dropout regularizes networks, so it prevents them from tracking the noise by randomly removing neurons. The idea is to encourage identical representations within the network by forcing the network, or by stopping the network from relying on specific neurons. So in one iteration, so in one training, when one update, the network was going to be, people are going to give the network this layout. So now this gradient step will optimize these neurons that are still active, so that they don't have a cross, to solve the problem. And then in the next update, another set of neurons will be randomly removed. And this forces the process to create similar structures in the network. And this, at the end of the day, is going to make the resulting network more reliable because it has a redundant set of subnetworks that can solve the same task. And the idea is that if one subnetwork gets it right, then probably the committee, so the combined version of it, will also get it right. And this is, you'll find this implemented in major frameworks. Typically, people use lower rates. So there's a probability for every neuron to be removed. And people typically set it to 0.2 for input layers. Because if you remove something in the first layer, say this was your first layer that had access to the input X, you don't want to drop out neurons here, because then you're removing access to the input data, and that just slows down the whole process a lot. But in higher layers, it's actually beneficial for a regularization, from a regularization point of view, to drop out neurons. So there people set it to 0.5. And then we can never, ever forget to remove dropout when we're done. So during testing, dropout has to go. And if we give our network to somebody else for production purposes, then also we don't want dropout to remain there. So this is something that has to go after training. Okay, and then finally, there's batch norm, which is the most recent version. And the idea is to apply normalization, not just in the inputs, but also in intermediate layers of the network. The idea here is that if we optimize a deep network, then the input to later layers changes depending on the earlier layers. This is perhaps this is obvious, but it's a problem during optimization, because if let's say we have computed an update, we apply the update, so that means we have changed the first layer. What if that means that our updates to later layers no longer make sense because the input distribution to that layer has changed because we made changes earlier in the network? And batch norm attempts to make this easier by restandardizing our distributions after every layer. But since we still want to be able to rescale things, this is now a learned parameter. So this, what is this, a gamma and beta, they are optimized to be able to rescale the data, but it's in an explicit fashion. Yeah. So this is something that you'll see often in modern networks. And I think the key idea is to take what worked well for the inputs, standardization, and apply it within the network everywhere. Okay, so that brings me to the summary of the regularization part. Sometimes regularization is required, but before spending a lot of time on regularization, we should consider reducing the model size. There's typically already a regularization in the literature specific to your field. So it's often a very good idea, if you are using a machine learning model, or if you're looking for a machine learning model, to look in the literature. And chances are that somebody else has already looked at a network. And if they've considered a regularization method, you can use theirs. Right, so typically there's a regularizer already built in. And if that's the case, then stick to it. Okay, so that concludes the talk on advanced optimization. And now I would like to give the floor to Lokesh to introduce units.